second speaker is Sergei Zuyev from the University of Gothenburg, and he's going to talk to us. Chalmers University. Chalmers University in Gothenburg, yeah, okay. Thinning stable point processes.
Okay, good morning. And thank you very much for the organizers for this fantastic workshop. I really enjoyed just every talk, and I think it's probably the most representative meeting of the last years. So, okay, what I'm going to present today is a work with of three authors, myself including. So it's Yuri Davidov from University of Lille in France, Lille 1, and Ilya Molchanov from University of Bern. And I will. So the title is Thinning Stable Point Processes, and I also mention the possible applications to telecommunications, but I will start actually from quite far, discussing with you stability notion and probability, and then gradually moving towards, say, from classical stability to non-classical stability. I would say quite interesting to my point of view, exotic stability models, and then going forward, passing to the stable random measures, and finally finishing up with stable, in some sense, stable point processes. Right, let's start from the very start, from the very beginning. So the notion of stable random vectors. This notion of stability was introduced by Paul Lévy, and the, say, a random vector, or say, well, distribution of it, so law, is called, well, generally in the Banach space, it's called strictly stable with, oops, it's not the wrong button. Okay, yes. It's called strictly stable with characteristic exponent alpha, and we will notate that as st alpha s. If for any t lying between 0 and 1, any number, we have the following equality in distribution and in law. So if we take three independent realizations of random variable, say, let me call it variable, random variable xi, so xi prime, xi2 prime, and xi, if we scale the first one by the factor t in the power 1 over alpha, so this exactly this very same alpha, and scale the second one with 1 minus t power 1 over alpha, then this sum actually distributed the same way as the original random variable. So since it is really the basis of all today's talk, let me just write this down. So, strict stability means that for every t between 0 and 1, we have this property. Okay, so of course the example that you all know, the normal distributions are strictly stable with parameter alpha equal to 2. Okay, so where it comes from, why it is important to consider stable objects? Well, because actually it inevitably arises in all kind of limit theorems. Well, say let's consider, say, the classical, very classical setting of the sum of IID random vectors. Well, let's take the expectation, say, be 0. Let's assume anything that we need. So if we denote by Sn the sum of n first terms, and if there is a random variable xi such that the sum of n terms normalized by this factor n in the power 1 over alpha converges in distribution to xi, in this case, actually this xi must be alpha stable. Why is that? Well, we say also that in this case the zetas, or the distribution of zeta, the law of zeta, belongs to the domain of attraction of the law of xi. So why is that so? Well, it actually, without, say, going into much details, the idea is very simple. So if you take, if you consider this scaled version of the sum, So let's do some simple arithmetics. First of all, let's decompose it into two subsums. So the first Tn terms and the rate, the last what is left is 1 minus Tn terms. Okay, again, ignore that, say the number n should be a discrete number, of course, but well, basically this. And then just by rewriting here, first of all, of course, the sum decomposes into two sums here and there, and then well, just putting up the right term here, Tn there in 1 minus alpha, of course, it should be compensated by this factor there. 1 minus Tn will be compensated by that, so it's exactly the same. And we see that, well, if there is a limit, so this guy will converge to the same kind of distribution. So this will give us psi prime on the left. This will be the coefficient. This will give us another psi realization of psi. This will be psi 2 prime. And say, of course, this will give us psi in the limit. So this is why actually, as soon as this random variable exists, in this case, it must be stable with parameter alpha. Of course, against case of alpha equal 2 corresponds to the classical normal limit. All right, okay. Right, so what is available? So should not give a lecture on, say, basic probability, but say generally in Banach spaces, not necessarily for the case of just random variables or random vectors, there is a complete characterization in terms of characteristic functions. So characteristic functions are these, say, B's expectation of exponent of the product, scalar product of z. So this is a function on z. Z lives in the linear functional. Then complete description of the domains of attraction in terms of the tail behavior. So how the tail of the distribution of these zethers should be in order to have convergence to the corresponding law. And something that is less actually known, or at least less known to say non-specialists, is the so-called Lepage representation for stable random variables, standard random elements with alpha strictly less than 2, so non-Gaussian case. So let me just briefly describe what this Lepage representation is. So actually, it says the following, that non-Gaussian laws, so with alpha strictly less than 2, so in between 0 and 2, admit the representation as the sum of the points of a Poisson process. So, but this Poisson process, so this is just the shorthand, say, well, this integral is, well, Poisson process as a point process, it could be represented, it could be thought of as a counting measure. So actually what it says here, if we sum the points of this Poisson process, specifically constructed Poisson process, then this guy will be actually strictly alpha stable with parameter alpha. But, well, what kind of the process we need for that? It has quite a specific structure. This process P alpha, it has actually accumulation of points around 0. So it has infinitely many points in 0. So actually the intensity measure, so the only parameter of Poisson process is intensity measure. This intensity measure is looking like that. So let me draw it in, say, two-dimensional case. So it has accumulation. It has a pole in 0, and it decays actually in with the right tail. What I mean by the right tail, so actually it's if you take the polar coordinates, then in these polar coordinates, this measure, which is actually Lévy measure, will have the following form. So it is a product of where is it? Yes, of a measure living on the sphere. So there is a sphere here. So this is a sphere. So there is some measure living on the sphere, and the radial component has this kind of decay. So you see it's a product of the two. One is a radial component that has exactly this tail behavior. And another one is a measure, any finite measure on the sphere. So this guy, this measure that lives on the sphere is called the spectral measure. Okay, so this is a very nice result, and this is what is called Lepage series representation for alpha stable laws.
Difficulty for alpha equal to 2.
Pardon?
What's the difficulty for alpha?
Well, it just diverges as well for alpha greater than 2. The corresponding Poisson process, of course, you can construct it, but the sum will diverge. Okay. Well, it's actually, this guy always converges for alpha less than 1, strictly less than 1. For alpha greater than 1, you have to make centering. Okay, so, right, so you need expectation to be 0. Right, oh, forget. So this is a kind of a picture that I try to show you what this, say, Poisson process looks like. So you see, this is a kind of, here is this kind of a law that lives only in the first quarter. So we have here the part of the sphere, so some kind of function, spectral measure living there. So it's a kind of density that I have depicted. So you see there's more mass around these directions. And then, say, you remember that there is a pole in 0. The decay is, say, governed by r minus alpha of the distance. So we have more points kind of, we always have accumulation around 0, but the points has more tendency to be in the direction where the density of the of the spectral measure is big. Okay, so you sum up just ordinary sum of these things, and you will get, of course, a two-dimensional vector in this case that will be distributed with parameter alpha. Alpha here is strictly less than 1. Okay. Right. So actually, if we have a look again at the definition of stability, so what we actually need in order to define the stability. So there's basically, well, look again at this formula, the definition. So the definition relies on the two operations. One operation is the sum of random elements, and another one is this scaling, so multiplication by a positive number. So as soon as the phase space, so the space where the random element takes values, is having these two operations, in principle we could write something like that. Whether it has sense or not, well, we'll see right now, but say in principle, as soon as there are two operations defined, we can also write this thing. So that means that the notion of stability can be defined in any, well, in a convex cone. So what is convex cone? It's exactly that. So it is an object that is supplied with two operations. One is the semi-group operation, which is plus addition, and the second operation is the scaling. So kind of multiplication by any positive numbers. So as soon as we have these two things, we could write this down. Well, okay, we need some additional, say, continuity, stability. So, okay, it should be a topological, semi-group, etc., etc. Let me skip that. Okay, there are two special elements in cones. The one that is somehow responsible, well, it stems from the definition of the semi-group operation, and it is neutral element. So that means that it's an element that such that if you add it to any x, you will get x. So this is neutral element with respect to semi-group operation, with respect to plus. And another one is the origin. So this is something that related already to multiplication. So if you multiply a vector by a small number, it should tend to somewhere. So this somewhere, let's call it the origin, and let's call it 0. And we want actually, well, it's a technical condition, but to make the theory nice, we want that this origin is unique, actually. So whatever x you take, apart from the neutral element, multiplying by a small number will lead you to this 0. Okay, so it's not yet sufficient for the theory. Why? Because if you examine actually, you remember this idea when the stable vectors appeared. So what we've done, the first thing that we've done, we have decomposed the sum into two subsums, right? So in order to have that, actually, there should be a relation between the multiplication and the group operation, semi-group operation. So actually, this means that we need to have the first distributivity law. if you don't have that, you cannot write that. But that is not all. So this is, for the first thing, we need this property, you see. So A is here is 1 over n, 1 over alpha. But the second thing that we want, just kind of mimicking what we had before, we need to be able to rewrite the first term, for instance, like this. So what that means, it actually means that we need associativity of scaling. So this operation should be associative. So fine, so far so good. So actually nothing special. Of course, this is something that you probably want anyway. What is interesting, there is a second distributivity law. And this is this law. A plus b times x is ax plus bx. And this is actually, we don't need that at all. And this is what perhaps was not observed before. And this is not the case in Banach spaces, by the way. But actually, just getting rid of this second distributivity condition allows to construct still quite, say, actually very rich, say, examples of these stable random elements. So let's see. So first of all, if we do not require second distributivity, it's actually quite interesting what kind of things we get. First of all, 2x is not x plus x. This could be absolutely different elements, so because we don't have the second distributivity. But it's interesting that if you do have second distributivity, then necessarily the zero element and the neutral element coincide. So in principle, they may not be the same elements, and we will see it in example. Yes.
So E is the neutral element for addition.
Yes.
What is 0?
0, it is a limit for multiplication of a vector by a small number t. So it's well, we are in the cone settings, right? So this is our cone. So we have here the sum of two vectors, x and y, is still in K. So that's why it is a cone. And they also can multiply by t, and we will get to this 0. So this is 0, neutral somewhere. Okay, so also it's interesting that if at least one element admits the inverse, then this also implies that that the two special elements coincide. Just curiosity. Okay, so now we can define the K. So we have now a cone. We have a random element living in this cone. So, and we call this random element strictly alpha stable with parameter alpha, exponent alpha, if we have exactly the same thing. The only thing is that what distinguishes us from the situation we had before is that this multiplication and this plus, these are the operation that we have in this cone. Okay, so let me just give you some examples. So first of all, the classical case, of course, if this just falls here just immediately. So first of all, Banach space with usual addition and usual multiplication by numbers. So it is this case as well. And we know that alpha is between 0 and 2. 2 corresponds to Gaussian distribution. So R plus, okay, R plus just positive line. So here we can sum up the elements, but we cannot subtract elements, right? So x minus y may be negative, so we can only sum. But we still can multiply by numbers. And well, what's the difference between one and between the first example? Well, the difference is that you know, so from the classical, say, probability theory, that one-sided stable laws exist only for alpha between 0 and 1. Moreover, for 1, it's a degenerate law. It's just okay. So, so this is an example that already kind of approaches us to a more general situation. More exotic example. So if you now take also positive numbers, but you replace the max, you replace the sum with the max operation, maximum of the two numbers. Well, in this case, actually, you can compute you can characterize what are the stable distribution for this operation, and this is called actually max stable laws, and they are actually Fréchet with the corresponding density. And here, actually, alpha, so these laws exist for any positive alpha. Right. If you replace sum by, multiplication is just ordinary multiplication. If you replace now the semi-group operation by minimum, well, in this case, actually, there are minimum stable laws, which are also studied, and these are Weibull distribution. And Weibull distribution, it has this density there, and alpha actually here is negative. So the laws only for negative numbers exist. Okay, so even more exotic things that I won't be insisting on, but for instance, you can consider compact sets in RD. You take union as semi-group operation and scaling as a multiplication. Then, or for instance, you may take as addition, you may take Minkowski addition as a semi-group operation, and the same, for instance, the same scaling. And you see that in the first case, alpha is any positive number. In the second case, alpha is just strictly between 0 and 1. Or the things that we will be speaking a little bit later, the sigma finite measures. You take conventional addition, so you just superpose sum the values of the measures, but as the multiplication, you take the scaling. So this is the scaling that is defined by scaling actually the phase space. So C times measure is a kind of shrinked or extended measure there. So in this case, actually, any alpha would produce you a law. So there are laws for any value of alpha non-zero. Probability measures with convolution operation and addition and scaling as this one. Actually, this corresponds, is just another language for the classical situation. Nothing more, because convolution corresponds to the sum of random variables. So it is just exactly as 1. And we know that alpha is between 0 and 2. So of course, the first thing to ask, well, you see there's a multitude of possible values for this alpha. So what determines the range of alpha? And how much of the classical results still hold for these much more general situations, as you see? It's actually not the topic of my talk today, although I have spent half of my time on that. But let me just probably use this tribune to make an advertisement of the paper that appeared recently in the Electronic Journal of Probability. And it's, it's a long reading. It's 63 pages paper, but there are answers and much more to these questions. And just to heat up the interest to this paper, let me just kind of briefly say something. So let me tell you answer to the question 1 about the range of alpha only. So you may have probably zillions of explanations why alpha in the classical case is between 0 and 2. Let me give you just another one. So another one is the following. So actually alpha is between 0 and 2 because Banach space is a group. This actually guarantees that the range is positive. And the second thing is that the second distributivity law holds for this. So this is actually why it is strictly than 2, strictly or equal than 2. Why?
That it's strictly smaller than 2?
Pardon?
Why does this imply that alpha is strictly smaller than 2?
Well, you have to read the paper. Yes. Why, for instance, for the max operation as semi-group operation, we have this. We have positive things because actually the two special elements, neutral element and 0, which is just ordinary 0 here, they are coincide, but the second distributivity law doesn't hold. And why for the minimum we have negative values of alpha is because actually the two special elements, 0 which is 0, and neutral element is actually plus infinity. They are different. So this is why alpha here is negative. So actually the range of alpha is some very intimate characteristic of the cone itself. So actually it shows, it's a kind of measure of how strongly the second distributivity is violated. So it's quite interesting. And the sign basically, well, there are some conditions, but basically in most of the cases, the sign is defined on whether or not the two special elements, 0 and the origin and the neutral element with respect to the semigroup operation, are the same or not. So if they are the same, then actually this means that alpha is positive. Okay, so why all these things were actually possible to do? And we have already heard say candidates for holy grails for almost every speaker, so I cannot just refrain from adding another holy grail to this collection of holy grails. So actually the holy grail here in this theory is a Lepage representation. And actually everything boils down to this object P alpha that I had, that sums up the points in order to get this stable distribution. Because this object itself is stable, in the sense that its intensity measure, this Levy measure, is quite specific. It is scalable with the right order when you multiply the process. Multiply the point process means they contract all the points. And because of this power law along the radial component, it scales just exactly the right way. So that means if you scale this with parameter t minus alpha, and you scale another one with that, and you add these things up, you will get the same p alpha. And then, if you just now sum the points of these things...
You said to scale its probability.
Sorry?
You said if you scale its probability to the power 1 over alpha. You said this.
I said that.
Yeah.
I said nonsense.
It's coefficient.
Yeah, you scale it just by multiplying all the points. So you scale all the points, by realization, of course. Yes. So so if you now take sum of the points here, so you just basically put integral over there, you will get something that has exactly the same property, because the sum or integral is a linear operation. So this explains why actually, if you have this object, and sum these points, you will necessarily get alpha stable random element. The nice thing is that, of course, the Poisson process, for existence of Poisson process, you need really nothing. So in almost all spaces it could be defined. So that's why this generality is possible. The difficult part actually is show that every stable random element admits this. And we know that's actually not true. Gaussian processes are not like that. But okay, there comes the difficult part actually. You have to employ the machinery of harmonic analysis. And there is a notion of, say, Gaussian in the sense of harmonic analysis on semigroups. So the stable distributions without Gaussian component are actually in most cases represented this way. So right, that's what I just said. Okay, so let's now shift to one particular example that you will be actually appreciating along the lines as we go, because this is what I want to tell you is the special case of this, let's say, general cones in the space of measures. Okay, so we have some phase space, a second countable phase space, so quite general object. So X, and we have measures living on this space. Okay, so we have our X, and we have measures. So what are measures on that? So, well, non-negative measures. You can multiply measures by numbers, just by multiplying the values on every set. You can sum up the values on every set. Of course, it's still measures. The two things are measures. So it is a cone. So it is a cone, legitimate cone that I had before. So, well, so this is the cone of the measures. There are some distinction actually. There are measures which have infinite mass, and there are measures that has finite mass. Okay, in the spirit of what I have told you, I want actually polar decomposition of this cone. You see, because for stability, now I'm going to consider stable random measures. For stable random measures, I need kind of this polar decomposition because I want something living on the sphere and something that scales with the radius in the correct in the correct way. So I need to define a sphere. So well, it is quite simple what could be a sphere for the finite measures. So okay, so how can you identify a line going say from 0? So these are scaled measures, right? So measures multiplied by a number. So what kind of measure you can take as a representative of this line? Probability measure. Call it M1. So if I have here the probability measure, so of course multiplying by the number gives me a whole line like that. So this M1, these probability measures, these are part of the sphere. Okay, so let me put it there. So sphere on the space of measures. So what's that? Okay, so it is clear that probability measures can be taken like that. It's a little bit more intricate what to do, how to identify say a representative in the case where you have infinite measure. So how to find the right one? So it could be done by many ways, and we have found one of the ways, probably not the best one really. So you can actually consider the countable base of the topology on X, so B1, B2, etc. Then, well, okay, what we do, we append the full space X into this sequence, and then we consider the first index I, such that the value of a measure, generally infinite, is between 0 and infinity. So if we have infinite measure, then this first mu of B0 will be infinite. But then there could be some zeros, but sooner or later you will have some non-zero value of this measure on some of the base set. Okay, so we take this, let's call this first instance to be I of mu. So then we can identify this ray with the measure such that has the value 1 for this element. Okay? In particular, say for probability measures, what we would have, or say for finite measures, you will immediately have the first element here. There will be less than infinity, and it will be just the total mass, so it will be greater than 0. So in this case, this I is 0, and we have here mu of B0. B0 is X, so mu of X is 1. So it's a probability measures. Okay, so anyway, this is a construction that gives me kind of sphere. Right, now, as soon as I have this sphere, I'm in business. Okay, so right, first of all, a little bit about the measures. So if we have a space, so we're now considering elements, random elements in this space. So the cone is measures, so random element is a random measure. So I want to study what are the strictly stable measures in this cone. Okay, so measures, what kind of objects they are? They are actually identified by their finite dimensional distributions. So if we fix some say system of disjoint sets B1, Bn, just to take the values, this is a random vector. So if we know the distribution of that, we know the distribution of the random measure. And actually, just like in classical case, the distribution is characterized by the so-called Laplace functional, and it is a function which is defined on non-negative bounded measurable functions with compact support. So this h here is a function. So I will write, instead of writing integral, so which is long, I will write these, say, brackets there. So to denote the integral of h with respect to measure zeta. So you take this integral, you take exponent minus this integral, and you take expectation. So this is what is called Laplace functional. Okay, so now we call a random measure strictly stable if we have the same. So again, what is here? So you should think of that as, say, these are measures, right? So if you evaluate this on any set, you will get actually a strictly stable random variable. Okay, and if it is strictly stable random variable, first of all, this random variable is non-negative. And we know that non-negative random variables exist only for alpha from 0 to 1. So immediately we get that random measures, stable random measures, they only have alpha, range of alpha is between 0 and 1. Moreover, for alpha equal to 1, these are degenerate laws. So actually any number is strictly stable with parameter alpha, of course. So degenerated laws which are concentrated on these, say, constants are, of course, strictly stable distributions. So these are deterministic guys. Right. So locally finite. Okay, so the first theorem comes and says that actually this is a representation of a Laplace functional for strictly stable measures. And it has the following form. Right, it is the following form which is written here. So what are the ingredients of this representation there? Of course, this Levy measure. So first of all, this is really reminiscent of the classical situation for the n-dimensional vectors. And indeed, it will be the case when you plug h here, just indicate a function, not indicate a function, but the weighted indicators, the sum of indicators of the sets. In this case, you have just here the random variable, which is exactly the values of the psi on these sets. So you have a random vector, and of course, this thing boils down to the known representation of alpha stable random vectors here. But of course you have to work hard. First of all, yeah, now you may think, okay, you take a smaller and smaller partition of these beta of these sets, and you will get to something that is living already in not on RD, but D goes to infinity. So it actually lives where? It lives on this space of measures. Right? Our cone is the cone of measures. So remember that Levy measure lives on this cone. So actually this is what stays here. So we have a measure which is defined on measures. So Levy measure lives on measures. Okay, and this thing is homogeneous with respect to the scaling. So this is the fact that still holds. Well, it's not very easy actually to prove this theorem because, well, first of all, it's easy to prove that the measures given by this Laplace functional will be stable. The other way around is difficult. The other way around is actually stems from this 63 pages paper that I mentioned. Because actually, yes, there is a representation of this kind of form for Laplace functional, but this Laplace functional actually, this measure lambda, Levy measure lives actually in the second dual space, so the space of characters on characters. And there is some additional, say, heavy work to show that actually this could be brought back to the original space. So this is the difficult part, and it stems actually from the theory, from the general theory. So this is the main, so the main theorem of for the random measures, stable random measures. Okay, so let's now, yeah, of course we can play exactly the same game as we had before, since the measure is homogeneous with the right order with respect to this multiplication. So actually what is sufficient is to define the measure on the sphere, and the radial component will be exactly the same. So that's what we are doing here. So actually alternative representation is the following. So the Laplace functional random measure could be represented in the form of, say, again, integral to the power alpha. And here, this is spectral measure that is living on the sphere, on the measures. Sphere is living on the measures. Okay, so that's another thing. But well, there's additional thing that this spectral measure should satisfy. It is this property. And put this down. So because it's important. So the integral of mu of b, so in the power alpha, sigma d mu should be finite for every Borel set B. Okay. Right. Well, it's time for example. For instance, okay, so you see, as soon as you have a measure, as soon as you have a finite measure on the sphere, so a measure on the measures, on probability measures, the simplest case, you immediately get actually the corresponding alpha stable measure. So the simplest way perhaps to generate, to think of such a measure, living on measures, you take just one measure mu and you kind of shift it with the help of another measure eta. So this will give you the say function, the class of stable random measures with this kind of transform. Well, in particular, this shifting measure could be taken Lebesgue, for instance, in RD, and in this case, you will get actually the stationary measure. Okay, well, that's an example actually. What is that? Yes, this is the Laplace transform of the value of the random measure on any set B. So you see, it has this form, and it's interesting that since alpha is less than 1, you immediately get that expectation actually of this guy doesn't exist. So the average mass attached to any set is either 0 with probability 1, or it has infinite expectation. So these are, say, particular, say, properties of this measure. Okay. And actually, it's interesting that there is a Lepage representation. So since it is a stable object in our cone, then there is actually a representation in the form of the sum of Poisson something. But this something, well, where these points of the Poisson process live on the space of measures. So that's actually is. So you take a Poisson process in this space of measures, so they all accumulate around this. So they are quite small here, and you sum up these, and you will get something that you will get. Yeah, the density of this Poisson process is governed by the Levy measure, and what you will get exactly this, say, stable random measure. It's interesting also that from here it stems that when it is almost surely finite, when actually only in the case when the Poisson process lives actually on finite measures. Because as soon as you have one infinite measure, just adding it to anywhere will immediately give you infinite measure. So actually it is finite if and only if the spectral measure that lives here, the spectral measure is concentrated on probability measures. Okay. Right. I will probably skip. There are some interesting object that is called independently. Yes. Okay. Stable random measures. These are something that has been studied. You take a book, for instance, of Samorodnitsky and Tako, and there is a chapter on stable random measures. So what is new? Well, actually, what is customary called stable random measures are actually random measures with independent increments. Because these are arising in stochastic calculus, and to make integrals you usually require that the values of the measure on disjoint sets are independent random variables. Here actually it is more general situation, and probably most general situation, you cannot do more. They are actually in general non-independent. But say to make a bridge to this kind of already classical situation, so it will be actually independently scattered if and only if the spectral measure is supported by Dirac measures only. So you see, well, here the probability measures, among them there are Dirac measures, just the ones which are concentrated at point X. So if you have this situation, if you only choose these Dirac measures, if and only if, in this case you will have actually independent scattering. So this is what corresponds to to this, say, vast literature already. Okay, now, right, yep. You can also characterize actually that there are some nice property like self-similarity, and let me skip that. Okay, so I'm coming to the last part. So the last part is the following. Okay, so we can do a lot of things for this situation, but, well, what's if, you see, we have to be able to scale the variable by any number t. But there are nice objects, some like discrete random variables. If you multiply discrete random variable by 0.5, you won't get discrete, well, you will get a random variable which is also discrete, but it's no longer, say z valued, for instance, right? So what to do if our space is discrete? So actually you cannot really multiply discrete space and get not discrete space. This cone is, well, it's continuous somehow. It contains all the lines. In this case, so first paper that we know, Stotelet and Varharn in the paper in the Annals of Probability in '79 suggested actually that this multiplication operation could be perhaps made stochastic. So think of, say, discrete random variable that takes values in n, right? So how would you multiply, say, this random variable by 0.5 and still get something that lives on 0, 1, 2, 3, 4, 5, etc.? Okay, well, what I suggested, okay, let's do the following. Let's just thin the points out. So with probability 1/2. So the formally you define the multiplication, say, of 1. So we are so our space now is just z plus, right? Natural numbers and 0. So how you multiply in this way by 1? So the result will be Bernoulli random variable with parameter t. Of course, well, you won't say the properties of the multiplication that I had before and say distributivity law. So that means that if you have t times n, so you have to sum n number of Bernoulli random variables, so you have binomial distribution. And obviously, well, if you have now a random variable that takes value here, well, just obviously, well, what this operation would be? It will be just the sum of that number of the corresponding Bernoulli random variables with parameter t. Okay, so of course the scaling means in terms of the distributions, it means that actually the distribution of the generating function of this guy will be written just this form. Okay, so since we have now this multiplication, well, there's no problem with the sum. We can define, or they define, the so-called discrete stable random variables with parameter alpha, or with exponent alpha, just by replacing in the definition this multiplication by this stochastic multiplication operation. Okay, and they have characterized actually what these distributions are. They show that they exist only, again, for for the values of alpha between 0 and 1, and their probability generating function looks like that. Function looks like this for some parameter c and this alpha. Okay, and DeVroy in '93 showed that there is a special representation of this in terms of the so-called Sibui distributed random variable. So Sibui distributed random variable has, it corresponds to the number of trials to get the first success in Bernoulli trials where the probability of kth trial decays like alpha over k. So the longer you are going, the less likely you get a success, but eventually you will get it. So this is Sibui distribution, and he showed that actually the discrete alpha stable random variables are representable as the sum of the Poisson number of these Sibui distributed random variables. Okay, but if we now start to thinking of what actually going on, so what is this operation? Operation is actually really filtration, so it's a thinning. You had a 1, you replace it with nothing with probability 1 minus t, and you retain it with probability t. So it's an operation that is actually studied in the framework of point processes. And that's why actually let's let's move to point process, because, well, this classical case of random variables is just also point process living on one point phase space. Good, so let's do it generally. And what we do, well, of course, the distribution now is characterized by the so-called probability generating functional, which is basically the same thing with the, again, Laplace functional of this, of the point process, but just thought of as a random measure. So basically, it's expectation of the product of the value of the function u on the points of the process, well, raised in the multiplicity. And of course, we do not want that this u is not one, say, apart from the compact set. So 1 minus u should be should have a compact support. So this is a thing, and of course the main thing that we have is a Poisson process, and for Poisson process, this probability generating functional has this form. Yes, and one more thing. So if this mu, the intensity measure of the Poisson, or say let's call it parameter measure, is random itself, so you will have to take additional expectation here with respect to this random object, and this is what is called Cox processes or double stochastic processes. So it's randomized Poisson processes. Well, the intensity measure of which is randomized. Okay, so well, then the thinning, the T thinning, so this operational thinning will just act on this probability generated functional this way. And of course, when x is just one point, we'll get exactly the same thing that is in the case that Sturtevant and Van Haren considered. Okay, now again, now we can call a point process discrete alpha stable or stable with respect to thinning if we have exactly the same kind of relation as before, but this say, new operation of multiplication. Okay, and the theorem goes that actually these processes, which are stable with respect to this thinning, are actually Cox processes, but driven by the strictly stable intensity measure that I just described to you. Moreover, the alpha is exactly the same. And PGFL, so probability generating functional, has this form. Well, I have already written in the form of that uses spectral measure. And moreover, say, well, the processes for alpha equal to 1 are exactly Poisson processes. Okay, so probably I skip the idea of the proof because there's no time left for even for ideas. Yeah, there's some work to do, but the main observation is actually if you rewrite the say stability in terms of the PGFLs, and you make this kind of change, you will actually see that it's exactly the same kind of relation that we had for the Laplace functional for the random measures. Now the difficult part is actually to show that this guy is a Laplace functional of something, because we had just formally defined that what y is a Laplace functional and y corresponds to something. So this is a difficult part, but well, it could be done. Okay, so let me just insist on a few properties of this. So first of all, there are infinite, so in every set, this point process has either 0 points with probability 1, or expectation of this number of points will be infinite. Moreover, this is the Laplace PGF of the number of points. So it has this form. And you see this guy that appears here, it's exactly this property on the spectral measure that must be satisfied. So this is why it's important, and so it appears here. Right. Well, we like avoidance probability in, say, when dealing with point process, which are the point process which do not have multiplicative points. And in this case, actually, well, they are characterizing distribution. In this case, this is this is exactly the avoidance probability for these processes. Okay, so right. There is one interesting, well, classical process which is called mixed Poisson process. So what you do, you take homogeneous Poisson process and you consider the Cox process where this homogeneous density, well, the density is just given by a random variable. So if you take this variable to be just random, stable random variable, alpha stable positive random variable, you will get the so-called mixed Poisson process, which is alpha stable. So this is probably the simplest example for this process. Well, now, in the last 2 minutes, I'm coming to telecommunications. Why is it always this important? Actually, it stems again from the fact that these things are appearing in the following limiting scheme. So you take a superposition of the processes and you thin them. So you consider this sum of, so you have some sequence or ID sequence of point processes. So you consider the sum and you consider the filtered version of that. So the theorem goes that this guy weakly converges to some non-trivial process. If this guy converges, then this guy will be discrete alpha stable with the same intensity measure. And moreover, this is a fact that was actually proved by Kallenberg. Exactly the same constants. If you multiply now the corresponding, well, where they are, the corresponding measures which are alpha stable will give you the same limit. Okay, forget it. So the same kind of coefficients will work for the parameter measures now, which are stable. Okay, so that's why, and as I have mentioned, these processes have infinite intensity. So if you observe the situation in telecommunications, point processes are used now widely to model something. So if you have some bursty behavior, or I don't know, people at the stadium watching a telephone, oh, so sorry, watching a match and phoning, so you probably want these kind of bursty models. So these are probably the good models. And I actually do not have time to say that these processes are actually cluster processes, and all the machinery of the cluster processes will work. And just let me show you a picture. Yes, and the clusters are actually something that seems to be new. So, right, let me show you a picture. This is a realization of this kind of process. So different colors correspond to different clusters. So how these clusters are obtained? First, we have a Poisson process living on measures. Okay, so well, on the sphere of measures. This is sigma. Then we take the points, so the points of this process are measures. And with respect to these measures, what we do, okay, we've got particular measure now, a point of this Poisson process. Now, we put Shibuya number of points which are independently and distributed according to this peaked mu I of the Poisson process. And we superpose these things. So this is how these processes are actually constructed. So you see there are some huge components that corresponds to these, say, huge values of the Shibuya number of points. But they all here they, I think that I have taken the distribution of the sphere that charges only, say, Gaussian measures, only shifted measures. So if you want, these are Gaussian kernels, and the number of points in every Gaussian kernel has this Shibuya distributed number. Okay, so yes, well, these guys are actually also infinitely divisible. So actually, all the machinery from infinitely divisible point process comes into play. So, so there could be, say, regular, the ones for which sigma lives on the finite measures. There could be singular, the ones where this measure lives outside on an infinite measure. So there are some interesting stuff that actually could be said much more about that. But I will probably skip it and stop here. Thank you very much.
Any questions?
Sergei, you have mentioned infinite divisible point processes. I don't know whether you find transparency with the Levi-Chinching representation for your alpha stable random measures.
Levi presentation. This is KLM measure, how it looks like.
You call it Lepage. So same discussion again, maybe.
Yeah.
So Lepage Levi-Chinching representation. So I just want to make a comment. Maybe it's also a question.
Lepage, well, there are at least two Lepage representations. The one is actually, I haven't probably really shown.
Anyway, I just want to comment on the fact that it appears to me.
Oh, right, like that. Will this do?
No, this. No, you have the generating function of a random measure.
Are you speaking about measures or point process?
Random measures.
Oh, random measures, so it is this part.
I just want to point out that if a random measure is infinite divisible, then you have this Levi-Chinchine representation. And in your case, at least it appears to me, it is the special property of alpha stable that forces the Levi measure to be of a special form. I just want to point this out. There's a theory of infinite divisible random measures.
Yes.
And what we have seen, it appears to me at least, is just a special case of the Levi-Chinchine representation.
Yeah, well, we have used that, basically.
And I don't understand.
Well,
why do you take so many pages to
I
get?
probably didn't pick up your point. All stable measures are necessarily infinitely divisible. For these, there are indeed the representation of the generating function. But in addition, you have this scaling property that
That's why
imposes additional this kind of tail decay on the corresponding measure. Yes, Levi measure. Yes, exactly.
That's
The one other historical comment seems the first case of this representation was in Chandrasekhar, 1942, when he wrote the gravitational force of a Poisson cloud in RD, and they found that the effect. So when you write for special values of alpha, you get, and he found that this is stable, symmetric stable.
Yeah.
You're saying that
So it was not Levi first.
What?
the first instance
First
of writing
I'm
a
aware
stable-
of this representation is
I think
1942.
it's before that. I mean,
You mean Levi representation or you mean Lepage representation?
I mean, what you call the Page representation.
What I call Lepage. Okay, so yeah, thank you very much.
any other questions?
About Sergei, about thinning. Thinning must be in the last question. Must be dependent. Yeah.
Yes. Well, actually, there is another operation that could be used. This is so instead of thinning, you can actually use branching critical, subcritical. Hold on. So the branching process with the number of descendants less than 1. So actually, sometimes you can give birth, say, for instance, for 5 guys who could be distributed, but on average, you should on average there should be less than 1. So this is more general case. Yes, we're considering right now.
You mentioned that these processes can be used as good models in telecommunications, so that kind of rise to the obvious question is how do you identify the various components of your models from the data?
Well, actually,
he said football matches and rock concerts, which I didn't see, but
we just started to discuss this thing, but it seems that statistics of this thing could be actually rather easy, just because of these GAN components that reveal immediately what kind of kernel you have, at least under stationary, say, assumptions. So basically, just observing this guy will tell you, but this guy just Gaussian, for instance. So it maybe not a big deal. But it's a kind of extreme value statistics, so we just started to look about that.
Thank you. Any other questions? Short question. Just very quick question. Okay, when you look at the definition of stability, you can write it in terms of, if you think of Levi processes, in terms of cell similarity.
It's a different thing. Well, I mentioned that. Yeah.
Okay, if you introduce an extra parameter,
Yes.
which is time. But anyway, maybe we should discuss that later. Okay, so let's thank the speaker.